Hello, everyone. My name is Ethan Ayari. I'm a physics graduate student here at the University of Colorado Boulder. And today I'm going to propose a possible dust instrument to explore some of the transport and loss phenomena for volatiles from the lunar permanently shadowed regions. So what we're going to go over is a little bit of background on the PSRs, a general overview of the proposed instrument, some numerical modeling efforts that have accompanied the instrument, what a simulated flyby for this instrument might look like, some of the details of its function, some legacy instruments that have either flown or will fly, and as well as a proof of concept that has been done at our lab here in Boulder. I'll move through this fairly quickly since it's been touched on in most of the other talks. For the purposes of this talk, the PSRs are craters in the lunar polar regions where they are deep enough that solar wind effects and other sunlight effects are not prominent. And based off of the results of an LRO, which have been touched on, there's an expected availability of water ice that remains to be explored. So what we propose is a time of flight mass spectrometer that would fly at a 100-kilometer orbit over the lunar polar regions. And the reason that we propose this is that interplanetary dust particle bombardment is a key possible attribute for how volatiles both evolve and are lost from the permanently shadowed regions. Since the solar effects can't be present, these impactors are a really key candidate for how the volatiles evolve. As you can see in the figure here, we have an incoming impactor and a resulting dust ejecta plume. And our goal is to have our instrument sample the resultant dust ejecta plume to make composition measurements. This is what a simulated ejecta flyby would look like. For this, we can assume a surface normal impact at x equals 0 kilometers. And our instrument, as I mentioned, would be flying at about 100 kilometers over the surface. So this in the bottom represents the resultant ejecta plume. We assume that post impact, we see two nodes. This is because we don't have a lot of surface normal in the angular distribution of the plume cloud. And when our instrument samples it, we would see these two distinct peaks from the nodes corresponding to it flying through either of them. I should also mention that our count rate is plotted in the marginals here for the instrument as it goes across. The details of how the instrument works. So we have an incoming dust particle. It'll impact a biased target, creating an impact plasma. And then using a series of biased ring electrodes, we create a focusing electric field that will guide the plasma ions onto a detector. They follow this parabolic trajectory, and the time of flight is related to the square root of the charge to mass ratio. So this will give us both mass and composition information. The reason that this reflectron style was chosen is that when the ions follow this parabolic trajectory, the initial distribution of the ion cloud is not included in the measurement. So the ions that are released more quickly from the cloud or more slowly will all arrive similarly on the detector. So we have both spatial and temporal focusing in addition to energy focusing. In addition, we design our ion detectors to have staggered gains. And this gives us a high dynamic range. That's because the time of flight mass spectra that come from these impacts will have both very large amplitude and low amplitude lines. So we want to make sure that we're capturing everything. A legacy instrument worth mentioning is the Surface Dust Analyzer, or SUDA, that will fly aboard the Europa Clipper measurements, the Europa Clipper mission, and it will make in situ measurements of the dust on the surface of Europa And it follows similar, or it wants to map similar ejecta on ballistic trajectories as seen in this figure. And you can see kind of what a resultant map from this instrument looks like with the space map here. So we can get composition as well as mass distribution. And in the case of SUDA, it also includes a velocity grid. So we can get some of the velocity information of the impactors. Here in Boulder at the Institute for Modeling Plasmas, Atmospheres, and Cosmic Dust, we have a dust accelerator. And so what we did is we took a prototype reflectron style time of flight mass spectrometer, and we used palladium coated opal just as a sample hydrated mineral. And we flew it at about 1.6 kilometers per second, which is the typical speed for one of these dust particles for if we were flying at about 100 kilometers above the lunar surface. As you can see in the highlighted box, water shows up. So it's kind of a proof of concept that we can make these measurements and that we can map the water. It's a little bit hard to see, but some of the other water clusters show up as well. So we can also map the evolution of those. While the dust accelerator experiments are informative and they teach us a lot about the instrument, they're also both time and money expensive. So to remedy this, a method to produce numerical spectra derived from the mineral, elemental, and isotopic ratios of the sample has been developed. Options to include instrumental noise and trends from the velocity and size distributions of the impactor can also be included. The hope with this is that we can expedite future calibration efforts, so we can make sure that the instrument is running properly with a simulated measurement as shown here. For the figure on the right, I simulated, thank you, a 1.6 kilometer per second impact of olivine peridot with instrumental noise added throughout. For the noise, I prescribed an SNR of 1,000. Having a tunable SNR is good because it'll tell us when our instrument is saturated to the point that we can no longer make measurements or determine composition. So we're hoping that this could be helpful for future missions with dust instruments. The conclusion of this talk is that the moon, like all airless planetary bodies, is continually bombarded by interplanetary micrometeoroids. The resultant injecta particles provide samples from the surface and an opportunity for dust spectrometers like the one I described to map the composition and identify possible volatiles from orbit. And then modern dust instrument technology like the reflectron style design that I showed is capable of mapping the PSRs in such a manner as we saw from the opal measurement. I would just like to say thank you to Mihai Hreni, Rebecca Mikula, Zoltan Sternovsky, Sasha Kemp, Frank Postberg, and John Hillier from the Institute for Modeling Plasmas, Atmospheres, and Cosmic Dust, as well as NASA and Serbia. Thank you.
All right, it sounds like we have time for questions.
David Kring, LPI. Where does the 1.6 kilometer per second typical impact velocity come from? Is that an observation or a theoretical construct?
Thank you for your question. So it's a theoretical construct based off of orbital dynamics as well as the ejecta model that I showed in that movie. So assuming the angular distribution that kind of is weighted away from the surface normal, what we might expect for some of those impacts as it comes back down from the top of its ballistic trajectory, as well as the orbital speed of the spacecraft.
All right, we also have an online question from Paul Lucy. Is it possible to determine D to H ratios?
What was that?
Is it possible to determine D to H ratios?
Thank you for your question as well. So we actually do have some folks in the lab working on the D to H ratios, but we haven't had any strong conclusions about it so far. So it's kind of still in the works.